Okay, that's working. So we got 20, maybe more. I'm going to share a screen. And then I'm going to pull up MATLAB. And y'all should be seeing a screen with MATLAB on it. Y'all see that?
Mhm.
Okay, now I had a problem. I've given you, this is problem 818, I believe, in the book. And if I can get it. Oh, this is a pain. Give me 1 second. This is homework 29, problem 818. I'm going to do this with MATLAB just so you can see it. I'm assuming it's going to pop up. Here we go. So here it asks you to find what X is. If this is, use MATLAB for this, if this is the impulse response, and then it starts at 0, and this is the actual output, the Y, and they want to do a deconvolution. We want to find X based on this. Follow me? Remember, this that I have that hand over is the impulse response. So it would be 3 delta of n plus 1 delta of n minus 1 plus 4 delta of n minus 2 plus 2 delta of n minus 3. If you wanted an actual numerical expression, you could take the Z transform of that if you wanted to go through the whole 9 yards of this process. But I'm going to do some out. This is the output in Y. So what I did, if you want to do deconvolution, I simply wrote down what H is. And if you look in your book, you should see this. It should say 3, 1, 4, 2. And then Y is 6, 23, 18, 57, 35, 37, 28, 6. Do y'all see that? Well, to do deconvolution, really in MATLAB, they may have a deconvolve function, but the way the book does it and the way I would do this problem is just doing it by first taking the effectively the Z transform and then making it an, really this is a fast Fourier transform, an FFT. If you take the FFT of Y, the output, now you think of it like you're in the Z domain, making Z equal to e to the j omega t, and then omega becomes a finite number of actual angles between 0 and 2 pi. Take that, and so I'm going to do the invert, I'm going to do the FFT of Y, and then I'm dividing it by the FFT of H. Now this is like you're in the transform domain. Remember, normally we have X convolved H is equal to Y. Here in the Z domain, it would be X of Z times H of Z equals Y of Z. And if you're talking about the DTFT, it would be the DTFT of Y divided by the DTFT of H to get the actual value of X. But since we have a finite series, we use the fast Fourier transform. So you take the fast Fourier transform of the actual output and divide it by the fast Fourier transform of the impulse response. But here's something important, the H, you have to increase the length of this. Remember, an FFT generally, and I'm going to do this with the doc cam here, if I can get it up. In general, when you have an FFT of anything, this would be like X of K, or a DTFT. What you end up doing is summing X of N, right, from 0 to N minus 1. Normally, we just go to what? N would be just the number of points in X of N that are non-zero, correct, class? You know what I'm talking about, right? Well, if you're going to do something where you're going to do an inverse FFT, then what you have to do is have the vectors the same length. So what we actually do is we're going to make N here to be the same length as our output Y. And then what you can see is because the 2 pi over N, now this is going to be a much smaller number. So when you index on X, the amount of angular change is reduced. All right. You follow me on this? In fact, what you end up getting is, I'm going to shut this down and show you. This will be useful later because you're going to be doing, everybody in this class is going to be doing stuff with MATLAB that involve this type of processing. I don't know if Jitendra Tugnate, Dr. Tugnate does this in COM. Reeves might have you do it in random signals and systems, but for sure in your upper level courses, you'll be doing things like this, either in MATLAB, Python, or Octave. So that's what brings us up. I take the inverse FFT, or I'm sorry, the FFT of Y divided by the FFT of H, adjusted to be length, adjusted to be the length of Y. Do y'all see this? It's the inverse FFT of H comma length Y. And then I have to take and get it back to the time domain. So I take the inverse FFT of that division, and I'm taking just the real part. I'm going to do a stem plot of it and also get the values. Now these values should correspond to what's seen. A stem plot simply plots, it just gives you a stem of the height of the actual value of X. You all see this? You've used stem plots possibly before. Can anybody tell me on Octave if it's the stem plot too? Anybody using Octave for this?
Yeah, it's the same.
All right. And does Octave, if you download the packages, I know you have to download a symbolic package. Does Octave also have FFT and inverse FFT? Can anybody tell me?
It does, but MATLAB got released school-wide for Auburn students.
MATLAB did what?
MATLAB was released to Auburn
Yeah.
students, all Auburn students.
Yeah, personally, because you have to have a FlexLM license, right? You have to still get the license from Auburn to operate it. So if you lose your internet, Octave's nice to have available, and Python as well. I'm learning Python, and there are so many things written for Python by users, frankly amazing. Okay, so that's that one, and I wanted to do that. Did anybody do this problem in MATLAB or Octave? Nobody?
I did it with Octave, but I used the deconvolution function.
There is a deconvolution function in Octave?
Yeah.
I wonder if there's one, is there?
I mean, it's the same in MATLAB.
Let me just see.
It's I think it's just like deconvolve.
I'm going to try something. I'm just going to do this. Take these values. And I'm going to run this. If you hit F9, with things you highlight, it runs it. So it gets rid of everything. Now I'm going to paste these values here into the actual command window. And I'm going to try this. So I'm going to say X equals, is it deconvolve? Is that what it is?
Yes.
H comma Y. I'm going to see if this works.
Wait, hold on. Look at the chat, Dr. Wiginski.
All right.
That's the functionality that okay, there. Yeah.
Wait a second. I got to find the chat. There we go.
It was spitting out the wrong vector.
QR.
So the
you have to put, literally, you're putting two values in here, right? Or is it, it's a return, and it's deconvolve UV, right? Isn't this what I did right here?
right, but like I was saying, like it spit out the wrong vector at first, and then it spit out the right one after.
I don't think that's the right vector, is it?
Yeah, I'm pretty sure it is.
Let's take a look. This is the right value right here. Oh, I guess, yeah, after 3, did it? Okay, so really you're just going, those are the values, right?
Yep.
Yeah, okay. So you can do it that way too. All right. Now that's not really that interesting, but any questions about that? You're going to be doing all sorts of stuff with probably, I'm going to guess, MATLAB and Python later on. And did Dr. New have you used Python at all for his class yet? Nothing? Have you used Python for any laboratory work yet? No, just MATLAB. You should be getting MATLAB in classes. Now, I don't require MATLAB homework pickup. some professors will. And in some of my classes, I do require, in EMAG 2, I have people do a MATLAB project that I give them, like for antenna, a beam steering, something like that. I will give them the parameters, and usually I use their name to define the actual angle of the antenna and the current. And so everybody's is unique. And I get some interesting codes, that's for sure. All right, that's that. Now getting back to, first, any other questions about the last homework at all?
I had a question about there was a like on some of the questions they would specifically say like this is the minimal.
Oh, it's phase minimum. That just means that the poles and zeros of the transfer function of H, follow me, are
Mhm.
all within the unit circle, H of Z, and that means it's stable. That's it. That's all that phase, minimum phase means.
So if it doesn't specifically say that it's phase minima, like you have to discern whether it's stable or unstable, or
Well,
can you just assume that it's stable?
I can tell you this. If I give you the pole zero constellation of a function, H of Z, say that, and I give you the scaled magnitude, you can assemble a function that would be H of Z. Do you agree with me?
Yes.
All right, now if you have that function, if any of those poles or zeros are outside z equal 1 of the circle, magnitude of z equal 1, then it is unstable. And then you may not be able to do inverse convolution.
Okay.
That's the thing with phase minima you can. You all know what I'm talking about, because if you flip H, say you've got, let me go here. I'm trying to not talk with my hands. All right, y'all can see that, right? Good. All right, if you have a function, that's the one circle. This is the z-plane. This is 1. Now, if I have x of z, h of z equals y of z, that's just the definition. If you take a transform of x convolved with h equal y, you will get this. Does everybody agree with that? Now, if h of z has zeros out here, then when I take x of z, it would be y of z divided by h of z, and the zeros would become poles. You follow me on that? And if you've got poles out here, it means this will not be a doable operation for most cases, but for a series that is, say, infinite. Do you follow me on that, class? It won't work. In order for it to be phase minimum, you have to have poles and zeros inside the one circle of your transfer function. You can play around with this but you will see that is a requirement for phase minimum. That's all it means. All right, other questions about the homework? Okay, I'm just gonna wait a second. Anybody got any other questions? And one last plea, if you could turn on your cameras, it helps me. But if you don't want to, I mean, I'm not gonna force you. It's nice to be able to see people, tired or not, shaved or not. By the way, don't think you're the only ungroomed bunch. In these meetings with presidents, people have got huge beards, their hair's, mine's shaggy, but people are just unkept as it can be. Some are, I haven't seen in pajamas lately, but we've had that happen more than a few times. Kids running around the background, dogs barking, birds chirping, the whole 9 yards. All right, let's see. Now, I said, Lydia, you asked for a circuits problem with.
It's a Fourier series, like
You
a
want-
frequency response.
You want to do Fourier series? All right, I'm going to just come up with a problem. This is like a typical problem. First, I'm going to do this. I'm going to say my x of t right here is going to be this. I'm not even going to spell out a function. I'm just going to give it to you. So it's repetitive. This is periodic. This is x of t. Make this value just be 2. Make the period be, say, 1. All right, that's x of t. With me? Now I got a filter. this x of t here is going to go into a filter. And this filter, I'm going to define in terms of a picture as well. This is going to be h of omega. And I'm going to show you h of omega looks like this. Let's say this is 5, and this is -5, and this is 1. So this is my h of omega. I haven't put down anything as far as a mathematical statement, right? I'm just drawing pictures. Can everybody follow me on this? And this is h of omega right here. And I'm going to put the phase of this too. So the angle of h of omega here, I'm going to do this. It's going to go from at -5, it's going to have a value of -pi/2, and it's going to go linear. And at 5, it's going to have a value of pi/2. Everybody gotten? Thumbs, people, give me an idea. I see some faces, but there's a lot more people out there. Aaron, do you get it? Then finally a thumbs up. So you are there after. You're in Georgia, aren't you, Dana? I hope I'm saying. This is I'm not going to be able to. I'll just leave this one alone. All right. Anyway, so how do I get the output y of t? I want to get y of t. How do you do that? This is a typical problem in a final. Where do you start?
Involve them.
Well, this is a. You're not going to convolve this, I'll tell you that. You could actually, to be frank about it, you could. But what do you do? This is a Fourier series problem. The very first thing you do is what?
We need to find the Fourier series for the one.
You're going to take x of t and turn it into a Fourier series. Let me tell you this. Go ahead and try to convolve this. You're going to have to write a series expression for that. It's an infinite series, all right? You're going to take a transform of an infinite series. It becomes what? It becomes a 1. It's going to have what? An infinite series will have a 1/t times an infinite summation of c of n times e to the j n omega naught t, right? And then you have to convolve those. Oh, you'll have fun. Enjoy yourself when you do. No, you don't do it that way. You first get the infinite series of that. You're going to get the x of t go. You're going to get x of t here becomes the infinite exponential series. Correct, class? All right, so how do you do that? Well, I know and I'm talking about this function x of t, but I will not be able to stay at that point. So I'm going to move this up here. Now, if it was a finite duration, I mean, it was something where it was non-periodic, then convolution would be acceptable. But I'd really do it in the transform domain first. I'd take the transform of the first function, transform of the second function. Then I'd multiply them, and then I'd take the inverse transform. Are you with me with this? And I'd probably do it in the S domain, to be frank about it. Unless the series, well, if it's a doubly infinite series, I mean, sorry, if they had negative values, you couldn't. You'd have to work in omega. Back to this problem. So I want to get the Fourier series of this. X of t is equal to the summation of, I'm calling it c of n e to the j n omega naught times t, where n goes from -infinity to infinity. And I want this c of n. Now, in the book, he uses an x of n there, but I prefer c of n because whenever I think about x of n, I think about a specific value in indexed in n that has nothing to do with the coefficient of e to the j n omega naught t. That's why I use c of n, okay? Everybody? Now, how do I get c of n? That's equal to what? 1/t technically, right? The integral from wherever I want to start to one period later of x of t times e to the minus j n omega naught t dt. Y'all remember that, right? Are we going to do this, class?
No.
No, what are we going to do?
Take the derivative of the graph.
We're going to take the derivative of x of t. And you've got x of t. Let me go ahead and just show you the derivative. So I'm going to take x prime of t. And what does that become? Well, it does what? let me do this. Make sure you do this when you're drawing this thing. This thing repeats forever, correct, class?
Mm-hmm.
So where I'm going to go from is a little before 0 in time to just before it shuts off. I'm going to go, that's my period I'm going to integrate over, okay? Everybody follow me? But I'm going to first take the derivative of it. So when I take the derivative of this, what do I get? Well, right here, what happens? If I take a derivative, what do I get from here to here? It went from 2 to 0, right?
That's
not
delta of -2.
right. So I get this, right? You agree with me, everyone? Now what happens? I get a
That's it.
constant value, right? Of what?
2.
Of just 2, right? And then when I hit 1, yeah, I get another delta,
Another.
correct? Right?
Mhm.
And then it stays constant, and then another delta. And then you all see what I'm doing here, right?
Mm.
Now, at this point, that's one derivative, right? I have a series of delta functions. So I'll call this my x1 prime of t. I want to get the coefficient c of n that is associated with that x1 prime of t. Is everybody with me on this? Okay, I'm trying my best to make sure you see me. And if I go too fast, stop me. Now, here, come on. This infinite series of delta functions will result in a c of n 1 prime of 1 over the period. What's the period, people?
1.
1.
1. And an integral from, say, minus 0.1 to 0.9, that's over a period, right?
Mm-hmm.
Of this function. Well, what are these delta functions? It's really -2 times an infinite series of delta functions of t minus really n, because the period's 1. And I have to multiply that times e to the, this would be going from minus infinity to infinity. I'm putting it in here formally, and then I'm going to make a comment where the only one you care about is when n is 0. That's the only one you care about. And then it's going to be minus j n omega naught t dt. Now, the delta function that you care about that turns on between minus 0.1 and 0.9 is n equals 0. So really, you can get rid of that and just say you have -2 delta of t. Do you agree with me, everyone? You all see this, right? Brandon, can you see it or not?
I see it.
All right, I'm just trying to make sure that everybody's can see this okay, because I wonder sometimes, because I get questions as if it's not visible in my other class. All right, if everybody can see that, what's this value going to be?
-2.
Just -2. And the reason is what? I have to evaluate that at t equals 0. The way you do a delta function integral, right? If a delta function is inside the kernel of integration, where does it turn on? It turns on at 0. You evaluate the functions next to it, and that becomes your coefficient. Correct, class? All right, so that means this is just -2. And therefore, what is Cn1, class?
-2 over j n omega naught.
Right. And what is omega naught?
2 pi
2 pi
f.
over t.
Oh.
Mhm.
Over 1, right?
2 pi.
It's just 2 pi, isn't it, class?
Mhm.
Yeah.
All right.
It's normally 2 pi over t, but in this case, t is 1, so it's just 2 pi, correct?
That's right. That's exactly it. Now I have that one. Let's go back to this function. This is a second function. Call it x2 prime of t, right? It's just constant 2, correct, class?
Mm-hmm.
What happens when I take a derivative of a constant with respect to time?
Get 0.
0.
0.
Don't-
So we don't care about x2 double prime of t in getting a coefficient. It's 0. You follow me?
Mhm.
Now, one thing we didn't do, we've got the C of n, but one thing we didn't do is what? We didn't get something for the series. What is it?
C naught.
Yeah, 0.
All right, we need to get C naught. What is C naught? Can you do it by looking? I got a height of 2. It's a right triangle. Therefore, the area is 1/2 base or 1 times height 2. 1/2 of 2 is simply 1.
1.
1.
You agree with me?
Mm-hmm.
Making sure everybody can understand that. C0 is 1, right? C0 technically is 1. It's 1 over t, the integral from 0 to t, x of t dt. It's just the average value of the function over a period, right, class?
Mm-hmm.
All right. Now I got to flip the page. So our series for x of t right here is equal to C0. Well, I'm going to just do it like this. It's equal for the sum of C of n e to the j n omega naught, which is just 2 pi, right? T from n equals minus infinity to infinity. But that's not the form I want. That's the exponential form, isn't it, class?
Mm-hmm.
I want the cosine form so it's an appropriate phasor relationship. Remember, cosine of omega naught t plus a phase angle. And the phasor domain is just what? The coefficient of the cosine, 1, at the phase angle, e to the j, whatever the phase angle is. And you get rid of omega t totally in the cosine form when you do phasors, right? I'm making sure, you all know what I'm talking about, right? With circuits problems, you didn't have 10 cosine of 377t plus 40 degrees and work with that differentially. What did you do? You put 10 at an angle, whatever it is, 40 degrees as your input voltage, and then the omega was used to calculate the impedance of the capacitors and inductors. That's how you did it, didn't you, class?
Mm-hmm.
All right, so for this one, I'm going to take this into a cosine form. So x of t here will be equal to C0. I'm not going to redo the cosine form because I've done that several times and you have it in your notes. Plus what? Plus a summation from n equals 1 to infinity, right? Of what? 2 times magnitude of C of n times cosine of omega naught t plus the phase angle of C of n. Do you all agree with that? Now, we know what C of n is, right? It's equal to 1 over j, and omega naught is 2 pi, right, times n, correct?
Mm-hmm.
That's also could be rendered as minus j over 2 pi n, correct?
Wouldn't it have been -1 over j and pi?
Yeah,
Yeah.
it should be.
What?
So it'd be,
Oh.
it'd be positive j over n pi. Because we had -2 over j
Yeah.
and 2 pi.
Oh, I'm sorry, minus 2. Sorry. I didn't put the scaled value. And it's minus 2, so let's be plus, and that's 2 there. I'm sorry about that. You're right. You all agree with that?
Mhm.
Now, you can see the 2's cancel, right?
Mhm.
So this is really what? It's 1 over n pi, right? At a phase angle of e to the j pi over 2, isn't it? In other words, j is equivalent to e to the j pi over 2 radians. Correct, class?
Mm-hmm.
Everybody see that? You got me on this one, guys? All right, now let's go ahead and I'm going to put that in here. So now I say my x of t is actually, C0 was 1, right?
Mm-hmm.
Plus summation n equals 0 to infinity. You're going to find out when you're actually modeling things, you don't need to take an infinite number of terms. 50 up to 100 terms usually does justice to a recreation of a waveform. And you found that out if you did the homework, that MATLAB homework, right? Remember, you took more terms, made this thing look more like the real function, except that discontinuities where you get that overshoot caused by the Gibbs phenomenon. You can never get rid of that. Now I have 2 times magnitude of C of n. Well, the magnitude is just what? 1 over n pi, correct? Right?
Mm-hmm.
And then it's going to be times cosine of omega naught, which is 2 pi nt, correct? Plus the phase angle. What's the phase angle of this?
E to the j pi over 2.
90 degrees.
Just,
90
just the
degrees.
phase angle is pi over 2. right?
Okay.
This is in radians, and I want to mention this term is radians, this term is radians. They're either both radians or both degrees, okay? Remember, 2 pi is 360 degrees. This would be 90 degrees, but then your cosine would have to take it in degrees if you're modeling, right? I always leave mine in radians because omega usually is in radians per second when it's defined. All right. Now, if I have that, I'm going to ask a question here that on the last test people had trouble with. If this is the expression for x of t, what is the magnitude of the third harmonic? So I want the magnitude of the third harmonic. Covered this in class. What does that entail? What is the value of n associated with the third harmonic? Anyone?
3.
3, right? Third, 3. N equal 3, third harmonic. When I ask for the magnitude of the third harmonic, you're looking for this. The coefficient right there when n is equal to 3. What's that value going to be? It would be what? 2 over 3, right? Pi. You all see that? That's the magnitude of the third harmonic. What would be the magnitude of the fifth harmonic?
2
2
over
over
5
5
pi.
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 That's it. I'm just making sure you see the association. What is the magnitude of the DC term?
1.
That's
Just
it.
one.
I'm just making you familiar with the terminology. When you hear that, you're just taking a look at what the DC term is. That's it. Okay? Now, having said all that, this is getting the function in the form we can use as an input. Now, you'll notice these are discrete frequencies, right? Let's take a look at that filter. I may have to adjust that filter because 2 pi n, see, this is omega right here. It's actually omega not n. Well, when I'm looking at this, 2 pi itself, I've got to admit somebody, hold on. Or can you admit him, Ruth? Or Lydia?
Okay.
All
Got it.
right, when you take a look at this, I chose -5 and 5. That was a bad guess. I should have gone to like, say, -10 and 10. Let's do it that way. This is my new filter response. I'll say this is my magnitude of h of omega. And I know 6.28 is about 2 pi right there, and -6.28 is about -2 pi here, right? You all with me? This is my filter response. It's a square filter. It's an absolute filter, and it goes to 0 outside of the range. And what kind of filter is this, would you say? This is h of omega. Class? Make that like one. It's a low pass filter, right? Because that's 0. Yes, it does. It is a band pass, but it's passing only low frequencies. So the terminology is usually low pass. Do you all agree with that? All right. Now I'm going to put the phase in this one too, so you get a look at that. So I'm going to say the phase goes from -10 to +10, and it goes linear like this from -pi/2 to pi/2. That's the phase of h of omega. Are you with me? Take a good look, everyone.
Yep. Can you slide it up just a little bit?
Yeah, I can. So. Are you with me? Okay. Now, I need an expression for this. What would be the expression for the phase? Is it a straight line?
Yes.
I'm trying to show you this is intercepts at 0. Do you agree with me? So the only thing you want for the phase, if this is omega, you want the slope times omega. What's the slope of this? It goes from -pi/2 to pi/2 over a range of pi, right? From -pi/2 to pi/2 is a range of pi, right? That's the rise. The run is from -10 to 10 or 20. So the actual phase of this would be what? It would be pi 20 omega, correct? You give me an omega, I can give you the phase. Do you agree with me, everyone? You have to be able to write an equation for a straight line. There's no exceptions. Do you agree with me?
Yes.
The x-axis is omega. Now we go and get our filter output. Now remember what this is, this type of system here. When we have it in this cosine series, what we look for is the magnitude and phase of the filter at these frequencies, right? How many frequencies do we have to worry about? We have to worry about DC, right? For sure, the C naught is a DC, or 1 is the DC term. Do you agree with me? You can even put down DC here. Agree?
Mhm.
Yeah.
Now, 1 times 1, the filter has a magnitude of 1 here. So the output is just going to have what? Y of t will just be, it's normally C0 times H of 0. The filter evaluated at 0, correct? But that's just going to be 1, isn't it? Correct? And if you remember the series, the output series, maybe I better write that down first. Y of t is actually equal to what? C0 times H0 plus the
Can you move it up a
summation.
little bit?
Yeah. It's C0 times H0 times the summation from n equals 1 to infinity of 2 times magnitude of C of n times magnitude of H of n omega naught, right? And then this is going to be times the cosine of n omega naught t plus the phase angle of C of n plus the phase angle of H of n omega naught. Correct, class? Do y'all remember that? That's the output series that we did. And you actually did some homework with that. You had some plots, but this is the functional form. Now, if you take a look at this for a second, you'll notice the filter is 0 after magnitude of omega is 10, right? And if you think about the frequencies, well, for n equals 1, it's about 6.28, right? It's 2 pi, correct, class?
Mhm.
N equals 2 is going to be 12.52, right? It's outside where the filter allows things. So the only term that gets through is the n equal 1 term. Y'all see that?
Mhm.
How many do with give me some indication of life out there besides. Thank
Say
you.
that again.
Yeah, the filter itself will not allow any frequencies greater than plus or minus 10, omega 10, right? Do you all see that? Right? And if that's the case, well, our frequencies start for n equal 1, it's 2 pi times 1, or 2 pi is about 6.28. That's this term right here and
Yeah, I
here,
get
right? Got it?
Mhm.
Now, what about n equal 2? Well, that's out here, isn't it? Isn't it, class? So
Right.
because you're multiplying by h of n omega naught, nothing but the first term gets through. So this is a real easy problem. Y of t, therefore, is simply equal to 1 plus 2. What's the magnitude of C of n? It's what? 2 over n pi, right? Isn't that right?
I thought it was just 1 over
I mean,
n pi.
sorry, one over n. So it's just,
Isn't it J over N pi?
okay, say it again.
Isn't it J over N pi?
But we want
But the
magnitude.
Oh, I see. I see.
So that's really 2 over what? N equal 1?
Yeah, so
Pi.
2 over pi.
Pi, right. Times cosine of what? Just 2 pi t, correct?
Mhm.
N is 1, right? Plus the phase angle of C of n, which was independent of what? N, what is it?
Pi over 20.
Pi over
Over
what?
20.
Phase angle of C of n.
Pi over 2.
Always pi over 2. That's C of n, isn't it? I'm not asking for the phase angle of the h of omega yet. I want to, but that's the original phase angle of associated with C. Correct, class? C of n?
Right.
It doesn't matter what n is in this one. Now I add the phase angle of h of n omega naught. Now you have an equation for that right here, right? That's supposed to be an omega right here, right? So you're evaluating this when omega is
2 pi.
2 pi, right? So this phase angle that would go here would be 2 pi over 20 times pi. Agree?
Mhm.
And that would be added right there. Then you would close that. Now, I didn't spend any time coming up with a functional form that would have a nice cancellation of pi, but I surely could have if I wanted to. All right, I could have had 2 over pi here and 2 over pi here, and then we get cancellation. But this would be the right answer for the input-output relationships of that filter. And we've gone and took the x of t and turned it into an exponential Fourier series. We got the coefficients using derivative action, right? And then we had to still get C0. After that, we looked at the magnitude of the filter at the frequencies, right, that would pass. All other frequencies we don't care about, correct, class?
Mhm.
And then we assembled the output based on this equation. And I gave you that information. I don't remember what homework it was. Now, how many understand this problem? And somebody will ask me in some way, shape, or form, would we be responsible for something like this on the final? The answer is yes. This type of a problem would be very typical.
This might be
Just ask
easy.
it. Just
This
ask
might be- but okay, so why is the magnitude from -10 to 10 of h of omega?
No. The magnitude
picked
goes
No, not the it only occurs from -10 to 10. I'm
because the
wondering.
filter only has a non-zero value for those in this range.
I think in your original one it was -5.
-5, yeah.
I expanded it because we would pass nothing there.
Okay, all right. So I'm gonna change that.
That's the reason I changed it.
Okay.
And so if the filter was wider, you would have to do superposition, right? You'd have to send.
You would have more terms. That's right. You would
Yeah.
sum all the terms that would be inside where the filter was. And this is a band. It's really a low pass. If it was a high pass filter, just high pass, then you would have an infinite number of terms. Right? If it was band pass, you'd have finite. Agree, class?
Right.
Okay.
Mhm.
Quick question. This may be a stupid question, but what would omega naught be for like the second or third harmonic?
No, omega naught never changes, right? It's n omega naught that changes.
So
N omega naught is the frequency. That is the omega, the transmitter. That's the phasor frequency, right? For the first harmonic, n equals 1. So it's the first harmonic, n equal 1, and this is just omega naught. For the second, n equal 2, and this would be 2 omega naught. For the third, n equal 3, and this would be 3 omega naught.
okay.
Follow me?
Yeah, I got it.
Okay. That's a very reasonable problem. It's something to expect on the final exam, some form of that. And it could be something where if I gave you the output, what input caused it? You'd have to, it's one of these things you have to be you have to understand Fourier series analysis, and you have to be able to work with it. If I just give you a filter in terms of h of omega or h of t, and I give you an x of t in terms of a drawing or a mathematical form, it doesn't matter. You have to be able to work with both. And to be frank about it, I would probably only be worried about getting the output y of t and the magnitude of certain terms, like the third, fifth, something like that harmonic, of the output and the input.
Dr. Baginski, could you walk over again just one more time how you got C of n?
Yeah. When I took my series here, original series, I could go right to the definition, right, and say the integral of 1 over t, the integral of this function times e to the j, or e to the minus j n omega naught t dt. But I don't like to do an integration by parts. So what I do is take a derivative of that, and the derivative of that is this, correct?
Right.
With respect to t. Now I can see I have a periodic function of delta functions, right?
Mm-hmm.
And that's what I want, because those delta functions have an associated C of n prime that just involves an integration of delta t times e to the minus j n omega naught t dt, which just evaluates the exponential operator where the delta function turns on. And that's how I got this. Right?
So in this moment, we're only focused on the delta functions. We're not worried about the 2.
The magnitude is 2. Minus
not,
2.
I meant the bars at the top.
This
The
one's
straight
a
line.
constant value, right? What happens, that is another function, right? Technically, it's another function, but what happens when you take another derivative of that?
It would be more delta functions.
No, it's a constant. Take a derivative of a constant, right? That's a constant forever.
Oh,
and
right.
ever.
Okay.
Zero.
Right. Okay.
and
that
then,
makes
and then that means the C of n2 double prime is 0, and 0 divided by as many j and omega naughts as you want is still 0.
Right. Okay.
But we still have to get C0 from the original function. That's the thing.
Hmm.
So if we had a circuit, like
Okay.
what we had in the last test.
All right. Then you would
So,
find the transfer function for the circuit, right?
okay.
How about, here's what she's really asking. I'm going
I
to
have a
go.
quick question about the previous one. Just if the original filter was -5 to 5 like you originally had it, the output would just be 0 because the
No,
filter
it'd be
would
1.
be.
It'd be 1. The DC term would
Yeah.
get through.
Only the
So,
DC term
so it'd
would
only
pass.
be the DC term there.
That's right.
Okay.
Right. And for low pass filtering, by the way, in general, when we do things with radar and we try to think of taking things down to baseband, you want only it's an equivalent to the DC term to pass. And that's for another day. But take the radar course, you'll enjoy. You'll get a lot of applications of this stuff. You'll see how come digital signal processing is so darn important. And if you guys, when I was your age, I was interested in high fidelity sound. Now you can do all sorts of stuff with writing codes for, they call them equalizers. That just changes the frequency enhancement, but you can do things. You can put echoes in, you can make it sound like in a hall. You can do a huge number of things doing digital signal processing in real time that make it sound incredible. As a matter of fact, a lot of places that broadcast and charge for it, like let's see, Sirius XM, there's I think a couple others. What they do is enhance the quality of the original sound system of the signal, I should say, of the music that they're broadcasting. So in your car, especially, it'll sound better. I don't know if does anybody use Sirius XM or been around somebody with Sirius XM? If you have it on, you'll see a difference in the sound quality of the songs you like when it's on Sirius XM versus regular radio. And they do it for a reason, because they want you to keep subscribing to it. Does anybody listen to Sirius XM besides me? I have it in my car. No?
Yeah, I mean, some family members had it in their car.
You can tell a difference, trust me. All right, back on track here. Now, so Lydia's question was this: suppose I have the same x of t as before, this.
Before some of us have to go for our next class, could you also go over one more time what all is going to be on the final?
Oh yeah, how time flies. Yeah, the final is going to have convolution, both discrete and continuous time. You have to be responsible. It's going to have matter of fact, how about this? It's going to have convolution, and it's both discrete and continuous. It's going to have Fourier transforms, Fourier series, Laplace transforms, DT-FT, Z transforms, all right, filters, and really the chapter 7 and 8 problems would be inclusive of these things. Follow me? And that's it. And so I'm going to say somewhere between 6 and 7 different problems, but there are multiple parts to each problem. You know how the tests are in my class. You probably can take a look at some of my old finals out there, but they'll be different from my old finals because this one will be open book, open notes. And I'd ask you to not use the internet, but there will be a lot of things that if you know it, you're going to fly through it and do very well. And if you don't know it, you're probably not going to have anything. I'm just telling you this much. Try not to cram. Get your sleep. It's at 8 o'clock on Wednesday, right? Isn't that right, class? All right. Now,
Pretty sure.
this is the thing. Don't just cram the night before. Go through, spend a couple hours a day from now till the final, reviewing things you don't understand, and then submitting questions if you need to. Put them on that GroupMe and Probably other people can answer them if I
So,
don't.
Dr. Baginski, do you have like another date to ask for like an extra session office hour
That's not
before the
bad.
final?
Let me, since it's on Wednesday, I figured Tuesday you'd want your questions. Right? Come on, man. All right. Let me take a look at my schedule right here. So let's see, that's this is Tuesday. I got President's Cabinet meeting. I don't have the Signals and Systems class, thank God. So I can delete that one.
It should be the 27th, not the 4th.
Right. I got an 20. I mean, I'm right. 28th, right?
Or yeah, 28th.
So 20. So far, nobody's stuck anything in there. But here's what happens. I'll get somebody from Samford usually when they see I don't have anything, because they look at all their schedules. And if there's a lot of people that can meet at the time, they'll just start sticking meetings in there. And I'd like to get them 2 weeks ahead, but they don't always admit. So why don't we do this? How about 11 o'clock on Tuesday? We schedule a Zoom meeting if you have anything. And can somebody, Lydia, why don't you send me a reminder like at 9:30 or so at 10, so I don't forget. But it's in there, my office hour. And I don't know if I put that in. I think that's in every one of these, but I'm not sure. Anyway, if you have questions, I'll try to answer them then, okay? But I encourage you to use GroupMe. I haven't been on GroupMe in forever, it seems like, and I really don't care how you act among yourselves. I'm not going to snoop. The provost reminded me it's probably better you don't. I got somebody got a question. Hold on for a second. I can't get to that chat easily. Hold on. So when is the test? It is on Wednesday at 8 a.m. And if you want to know how to get this, just type in final exam schedule at Auburn University in Google, and it will take you to a page. You'll have to log in with your user ID and student number or student, whatever your username is, and they'll have an exam schedule you can print out. Okay. If you're not familiar with this, can somebody just send him a link to the exam schedule where it is, please? I think you can put it in the chat if you want. Okay. Can you take care of that, someone? Lydia or Ruth, anybody? So I want to make sure everybody has this. And by the way, the students, a lot of students that transfer into a university don't know that the final exam schedule is available online. Those are the type of things that students that are here do. Even faculty don't know. Sometimes with new faculty, they have to ask the question. Any other questions? All right, some people have to cut out of here. I think, Ruth, you do or not? You do, and anybody else? That's the Fourier series one. I didn't get a chance to do convolution, but you know, convolution really is the flip and shift deal, right? It doesn't matter if it's discrete or continuous time. We're losing people, that's all right. I got somebody who wants to be admitted. By the way, if you guys do you have any suggestions before I hop on a convolution thing about how to better teach this, things I can do? I'm going to have this DocCam down as right here while I have more available. Anything at all? I don't really want to go to PowerPoint, but I might have some pre-made slides that I can reference when open the book and point at it. But besides that, I don't know what else I can do. I was actually thinking about this, if I could get a small whiteboard and then having this doc cam, not that doc cam, but a high res doc cam look at it. I don't know how you feel about that, but is this going okay so far?
Yeah.
I personally like the PowerPoint slides.
You want PowerPoint?
Yeah, I think PowerPoint would work well.
Okay.
I mean, as long as they're like, they explain the concept, then actually go over like, you know, like simple work examples or something like that. So like problems where you don't spend a whole bunch of time just solving problems, but you focus more on just the concepts.
Well, what I like doing myself personally, and I appreciate when professors do this, they can reference a formula, a slide, something that's on a pre-formatted thing, a slide. But when they're going through the problems, I like to hand work them. And if students are working along with me, it stays with them. And if there's something that doesn't make sense, they can ask it when they're actually doing it.
Yeah, I agree with that.
Now, there are people that don't do that. I don't think Gross does that, but I
Right.
think he just runs through PowerPoints, and that tends to numb the mind. It doesn't.
I don't
really
like
does.
that. I do like the worked examples, but yeah, I think the PowerPoint slides are good because it, you know, it has like a structured layout and it's easy to follow and go back and reference and things like that.
All right.
If you like have the PowerPoint slides up and then ask people to read them, then do some work theory in class.
Yeah.
If you're thinking about time constraints.
I can actually do that. That's not a bad idea. I think I can do that. Okay. I wanted to. Is there anything special you want to see? I was just going to do a convolution.
Someone asked in the group meet, is there going to be limited partial credit or no partial credit on the final due to it being an open note, open book exam?
Well, there's a lot less. There may be, I mean, look at the last test, I gave partial credit, all right? I wasn't going to at first, but the results shocked me. That was a very easy test in my mind. I thought there would be much higher scores. The final will be more comprehensive, but the same type of problem, same level of difficulty. It's not going to be over the top difficult, but it'll be something, if you know, it'll be clear. And if you don't, it'll be pretty clear to me too.
And it is representative of the homework.
Yeah.
It's similar.
Yeah, and probably in fairness, more difficult in general because you do have open notes, open book.
Right.
Most quizzes and tests, if you actually look at them, with a book open and just a fair amount of understanding, they're very easy. My quizzes and tests are trivial if you think about them. But if you're unfamiliar with the material, even with an open book, it takes you a while to learn it, and so you get in trouble. I do not like giving open book exams. I've learned my lesson with that. People get sucked into using all their time on one problem and reading about it. They get one done and 3 are left blank. I've seen that. So I don't like open book, open notes. I do sometimes give you formulas in the radar class because some of the stuff's pretty absurd. They're long and difficult. I'll give you that, and I may, with things like radar and electromagnetic compatibility interaction, because especially electromagnetic compatibility and interaction, then there's much more programming and actual taking raw data and sorting through it. Into, you know how we got X from a Y, right, by using an inverse operation, right? Well, in the real world, you have sensors. The sensors have a filtering aspect. They have an H of omega times whatever comes in, comes out. And so when you want to get what actually came in, the raw data, you have to invert that filter operator, whatever it is, and either convolve or do it in the frequency domain in inverse FFT over samples of time to figure out what, in fact, say the real radar signal was, the time structure of the real radar signal in terms of polarity, as well as frequency and magnitude. And then you can figure out, by doing more signal processing, what in fact's out there causing it. And for EMC, you can also do that. In EMC work, the problem is you don't know a lot of times what source is out there. You know, this is the signal you got. You may have 10 sources causing it. And so you got to go through your sort of detective work and figure out, after you do a whole bunch of samples, what the most likely causes are and then verify it.
Also, Dr. Baginski, after you finish the convolution question, could you do the circuit question again with?
Let me just do the circuit question right now.
Okay.
Because that's what I was trying. This is the X of t that we started with before the class ended and everybody bailed on me. Apparently, are y'all with me? That's the original X of t. We have the Fourier series of that, correct?
Yes.
All right. If we have a Fourier series of that, I'm going to come up with a circuit. A circuit, hopefully you'll appreciate. This is the input. This is going to be my X of t. It's a voltage. And this is my output, Y of t. All right. I'm just going to go ahead and let this capacitor be equal to 1/3. Make the inductor equal to 1 and R equal to 1. All right. That would be Henry's. That would be farads. And I want to know Y of t. All right. That's X of t. You got me?
Mm-hmm.
Now, we know R is R in the frequency domain. When I take this into the frequency domain, this would become J omega naught times N times L. That would be the impedance of that, correct, class?
Yes.
The impedance of this would be 1 over J omega naught N times C, or 1/3, or simply put 3 up here. And that would be X of C, correct?
Mm-hmm.
Y'all agree with me?
Yes.
All right. Now, if I want the filter output, what I'm really going to do is get the H associated with it, the transfer function, right?
Yes.
Oh, so my H of not omega, but N omega naught would be the impedance of this, which happens to be 3 over J N omega naught right there,
Mm-hmm.
right? Divided by that 3 over J N omega naught plus 1 plus J N omega naught, right?
Mm-hmm.
It's the ratio of the output impedance here across the capacitor over the total impedance, because this is simple voltage division, right?
Yeah.
Now, can you all see, I can play with this. If I multiply top and bottom by J and omega naught, gets rid of that, there's a J and omega naught here, and this would become what? Minus N squared times omega naught squared, right? Because if you have J and omega naught times J and omega naught, it becomes minus N squared omega naught squared, correct?
Mm-hmm.
Now you've got something, you can manipulate all that you want, but this is, if in fact, that is the magnitude. And the phase, of course, is something you got to play with a little bit. If you take it and multiply by J and omega naught, you would get this. It would be 3 over, and then this would be 3 plus J and omega naught. And then it would be minus N squared omega naught squared. You pick an omega naught, that's what you get, correct? Our omega naught originally was what? 2 pi, correct, class?
Mm-hmm.
Yes.
So if it was 2 pi, it would be 3 over, and this would be 3 minus N squared times 4 pi squared, right? And then plus J N times 2 pi, correct?
Mm-hmm.
I just replaced omega
And with
naught
2 pi.
with 2 pi. All right, now if you wanted the phase of that, say you wanted it for N equal 1. Remember in the filter response we had, it was only the what? The first harmonic that got through, correct?
Mm-hmm.
If you want the phase of that, what would you get? If N equals 1, my equation becomes 3 over, and it would be 3 minus, and N equal 1 is 1 pi squared minus pi squared. So that's going to be a negative number, right? This would be negative, and then you have plus J, and it would be just 2 pi, correct? If N equal 1. Agreed? What's the phase of that? You're going to have calculators available to you. Well, the phase of that would be what? Your calculators would do this in a heartbeat, actually. You would have a number 3 over something negative plus J2 pi. You could get the magnitude and phase from your calculators very easily. Do you agree with me?
So quick question, are we allowed to use a calculator on the test or no calculators?
You can use a calculator. I'm just trying to keep you off the internet. That's my, and I'm not going to go to HonorLock. I've decided that already.
Okay.
It downloads too much spyware anyway. You can, and by the way, I was told that the Chinese are actually the people that write a lot of this code, so they might be stealing your bank account information, this stuff too. I just don't, I'm not going to ask you to use iron lock. I'm telling you that right now.
Okay, that's fine.
I'm just,
Okay.
I'm trying to keep you, as honest as I can. So everybody's camera's going to be on. You have to be visible. And I'm just hoping you do what.
So, a quick question. The reason why you set n is equal to 1 is because that's the DC component?
No,
Or
DC component is
is
n
it
equals 0. N
n
is
is
0.
equal to 0?
Yeah, that's just the constant value. Remember,
Okay.
I'm doing this. This is the filter response. Now, frankly, if you look at this, this has a continuous, this does not go to 0 at any point. This thing has values, some finite value for all frequencies. Do you agree?
Mm-hmm.
All right. I mean, as it goes to infinity, it goes to 0. But really, this is a type of low-pass filter. All right. It actually have 40 dB of roll-off instead of 20. But when you take a look at this right here, if I wanted in an equation form, you could do it. And if I wanted to know what the third harmonic was in the output, then you would do what? You would take 2 times C of 3, right? The magnitude of C of 3 times evaluate this magnitude at n equals 3, correct?
Yes.
Right.
And you'd multiply those together. That would be the magnitude of the third harmonic of the output.
So I have a, well, so I know this transfer function, it changes with
And
each harmonic, right? So how would you do it with a Fourier transform? Would it just be h of
no.
omega?
This is which you'd have to, if you wanted the Fourier transform, let's do it with S. Normally, the way you do filters, continuous time filters, is this. You're going to have an X of T becomes an X of S. Then you would have your resistor R, your inductor L, and your capacitor here, but you put in the impedances. This would be SL, and this would be 1 over CS. Right.
Okay.
Now here's the output, right? Y of S. I can take a look at
slide it down just a touch.
Yeah, I can take a look at Y of S over X of S is H of S. That's what I always am up to. And I can take a look at that. That's 1 over CS over 1 over CS plus really R plus SL, correct?
Right.
Now you need to massage this a little. So multiply top and bottom by CS for starters. And I get 1 over 1 plus RCS, right? Plus S squared LC, correct?
Yep.
Now, you don't want that S squared to have any kind of a coefficient if you're going to do inverse transforms to get H of T. It's sufficient the way it is if you wanted the filter response, because then you would first let S equal to J omega, and then you would let omega become Jn omega naught. And the N indicates the order of the harmonic, first, second, third, or which harmonic it is. But just to do this, because this, you don't use a Fourier transform per se, you use Laplace transforms when you're doing this work, usually.
Right.
And to be frank about it, usually a thing like that, you want the coefficient of the highest power in the denominator to be 1. So you divide by LC, and then you get 1 over LC, S squared plus, and then this right here is going to be R over LS. And then finally here, at the end, it's 1 over LC. And that would be your H of S, right? Y'all with me? Now, this is in the form that you see in your books, whereas a constant K, S squared plus, and it's usually a damping factor. I forgot the symbol that they put, something like that. S plus omega naught squared. That's the form like in the circuits books. And when you get laboratory work, they're going to say that this is a standard form. The omega naught is always created by the product of L and C. 1 over L and C is omega naught squared. That's the resonant frequency that you've heard about, right? This coefficient, this R over L, is called a damping factor. And the value of that tells me whether I have 2 poles that are unique. So I'd get an overdamped response, 2 exponential responses. If I have a single pole that's a double pole, where you would have S plus, really S plus a constant squared, just 1 pole squared, right? Or if you have complex roots, where you have really S minus pole 1 times S minus pole 1 conjugate. So you got 3 possibilities. And I think I went through this, right? Remember I went through the underdamped, overdamped, critically damped, right? Now, that's continuous time looking at a filter. When we're doing a periodic function into a filter, then you have to take this form, any form really, and you let S become J n omega naught. And then you evaluate both magnitude and phase at every value of n. Okay?
Okay. Dr. Baginski, I'm still a little confused about the phase aspect. I understand the magnitude. I think I
Why don't we
get
do
that,
this?
but
We'll just talk
still
about
unsure.
reality. Suppose I had 1/2 minus J6. What's the magnitude and phase of this? Call that C.
Okay.
All right, the magnitude of C is what? 1/the square root of 2 squared plus 6 squared, isn't it?
Yes.
Do y'all agree with me there?
Mhm.
That's magnitude. What's the phase? Well, if I look at this, the phase that the bottom part, the phase of C would be equal to, well, the phase at the top is 1 and an angle is 0 degrees, right?
Yes.
It's 0. Downstairs, what's the phase? The phase would be what? Take a look at this. This is -6/2, and just plot that so you can see it. -6 is down here, right?
Mm-hmm.
And it's over 2, and then 2. Well, 2's up here, right? Can you see that?
Yeah. Oh, I
So-
think I have my axes backwards. Whoops. Okay.
All right. So, oh, I'm sorry. I've got that
It is
wrong.
back. Yeah, those
Yeah,
axes
that
are
is.
All
back.
right.
Let me. I drew it wrong.
Yeah,
Let me
the
go
J
here.
is the Y.
And
Y
this
axis.
is 2, and this is, sorry, this is -6. My bad. -6, right? So the actual phase is this right here, right?
Mhm.
And it's negative, right? So it'd be minus the inverse tan of 6/2, correct? Opposite over adjacent, right? And that
Mhm.
would be a negative phase angle there, right? Y'all see that?
Yes.
Now it's a negative phase. Now, whatever this is, the phase angle here is minus tan -1 of really 3, right? You agree with me?
Is there a reason that it isn't a -6/2?
Well, 6/2 is 3.
It's negative.
If you would no, if you wanted to do this, you could put -6/2 in your calculators and you get the
Okay.
same angle. I just
Mhm.
popped the negative out.
Okay, okay.
I don't want to mess with it. So it's this. Now, what happens when this comes on top? If I have -30 degrees in the denominator, it comes to the top, the numerator becomes
Positive?
+30, right? So
Yeah.
this really can be written as, get rid of that, it's just the angle of tan of inverse tan of 3 would be the phase.
Since 1 is at an angle of 0 because it doesn't
right.
have any imaginary components.
Right. And
And
if the top did have an angle, you would add that to it.
so you would add them instead of multiplication?
Yeah. And you know, when you think of phase, what do you really think of? You think of some magnitude e to the j some angle, right?
Yes.
All right, let's take this times b e to the, call it θ1, e to the j θ2. Well, what is that? The product. It's a times b, e to the j θ1 plus θ2, because you're adding the exponentials, right?
Yes.
Okay, that's what you do.
Okay. All right. Interesting. Okay, that makes sense.
Everybody here is in Auburn. Chris, are you in Auburn?
Yes, I am.
So this is the Auburn crowd. Y'all can probably Zoom.
Essentially.
You know, you can do Zoom meetings with the students, by the way. I don't know if you've tried that. Zoom's free, right?
Yeah, we've been doing that to study.
Yeah, we use it for studying.
Excellent.
The only issue is when you have more than 2 people, it limits you to 40 minutes per session.
Oh, really? Discord's pretty
Yeah.
good as well if y'all want to try that out.
Well,
You said which one?
Discord's really good at like multiple video hosting.
can you send me that link, Lydia? Or post it? Or yeah, just
Yeah, Discord's really good. Me and my wife both use it for gaming.
there's a thing called meeting to or go to meeting or something like that too. Covenant Presbyterian Church uses that. I've been going to virtual church.
Yeah, I know with Zoom you have to have a license. If not, then anything more than 2 people in the meeting limits you to 40 minutes.
That's all right, though. If they cut out, just cut back in.
Well, that's what we just restart the meeting like 7 times in a row.
If you have that long, 7 times 4 is a lot of time. But Auburn
That was
University
only one
has-
session
Now,
this
Auburn-
semester.
Auburn University has a license, so you may very well be able to go there and use the Zoom license software to do your Zoom meetings. Somebody else, hold on. I don't know who that is. Lydia, did you let him in, or who was it?
I don't think that
I think
anyone's
that was
coming in.
just a chat post.
Yeah.
Oh, okay, but sorry. All right.
So, Lydia, for Discord, do you have like a private, like a server that you host?
Mostly, I think they allow up to like 50. They increased the number of people that could be on a server and be in a video call since the coronavirus. And I think it's like up to cap is 50. I'm
You
not
can
sure.
you
For a
can do
video
it
call.
multiple ways. For a video call, you can just simply call a person
I'll
on
be
their
right back.
profile.
I'll be right back.
And so that way there's no server even involved. But that is true that I think you can do it through a server.
Mhm.
I
Oh,
don't
yeah.
do it through a server. I just do it through personal
It's been a
calls.
while since I've used Discord. My wife uses it all the time for her video games, but I still have it, but I just don't really use it.
Yeah, I
I
got.
didn't know if you could post the link to your server or whatever in the group me or something.
I think I can make one. Probably.
It's not hard.
Yeah.
It's very simple. And if you want me to make it, I can. I have like 4 or 5 that I have
I mean, it
created
shouldn't take too long, like
now.
2 minutes.
Yeah, I know.
Probably.
Like I know that somebody, I think it was Ruth, a while back had posted like the Discord server for like engineering or something like that. But I went on there and there's like 4 people on there, and nobody ever says anything or posts anything, so I have no idea. So I didn't know if over the next week or so when we study, like if it'd be easier to do that than try and reset Zoom all the time.
Okay. Yeah. Yeah, I didn't know that Zoom had like a limit to it.
Yeah, like when me and Chris would study, just us two, we could go for hours. It was fine. But when it was like me, Chris, Ruth, and I think it was like Jacob or somebody else or something, we had to keep restarting every 40 minutes.
Gotcha.
So
Okay. I'm posting a link in the group me right now. So hopefully, I don't know if you can make like a permanent link, but this one expires in a few days.
let me see.
Hey, do any of you guys know how to do the partial fractions with the derivative method?
Beginsky explained it once. It's been a really long time since I've looked over it.
So, Lydia, you can set the invite to not expire.
Okay. Let's see.
So in the top left, it should, Signals Study Server, the click invite people, and then there's a link, but then under it, it has edit invite link. And you click on that and set expire to never, and then generate it. If that makes any sense, or I can do it because I think the permissions are built that way.
What was it again?
I've got it. If you just want me to send it,
If you would like.
okay, I'll do
Yeah,
that.
I don't see anything in the group me.
Because I didn't post like the temporary link yet, so I think
I got a quick question.
Nick's got it. So if he would
Mhm.
like to do that, it's
Yep.
fine.
Yeah, if you just want to post like the permanent link or whatever. I don't know. I never hosted any channels or servers or anything else. I always joined other people's, but my wife probably knows more about it than I do.
I should probably change the logo. Whoops, hold on. Or the icon. Ooh,
All right, that should do it.
Yeah, signal study server.
Mm-hmm.
Yep.
Yep.
Of course, Discord's got an update.
But yeah, we'll see if people end up using it.
Yeah.
I don't know if they will or not.
I have
but-
no clue.
Yeah, that'll work. So yeah, I joined into it now. So
All right.
Did you send me that link, or did you just put it in chat?
I put it in the group me, but I can put it in here as well.
Or just email it to me if you don't mind.
Sure. Yeah, I can do that.
All right, great.
thanks.
Hmm.
So Dr. Baginski, to be in the Discord, it'll have you make an account.
Okay.
But that's pretty simple, just an email and a password. So just as a heads up.
What I'm really thinking about is I want options available until in case Zoom gets knocked out.
Mm-hmm.
I mean, I've had some problems. It's been pretty good, but I've heard from other people that they've had problems with people, I guess, hacking and crashing meetings. I don't know how much of a problem it is.
Yeah, I mean, I've seen some stuff about it or whatever, but the nice thing I like about Discord is the push to talk option. So like you can hit, control or whatever to allow your, like basically to unmute yourself whenever you want. So
Right.
makes team communication, especially for video games, a lot easier.
I haven't.
People don't really talk much in Zoom anyways, so I don't imagine that it would make people talk very much more anyways.
About the only game online I've been playing more of, I think, is chess. And learning chess strategy.
Never
Dr.
really
Baginski,
did that.
Hmm?
have you ever looked into Go?
What is
No.
it? Oh, the game?
A game,
wait.
yeah. It's like
I know
you do know Go? Okay.
it's Chinese, right? You're talking about-
Japanese.
or Japanese, whatever
yeah.
it is. Yeah, I know. I believe I've played that game a couple of times.
Okay.
But it's a game of thinking about the end from the beginning. You're trying to capture as much as possible. Yeah,
Right.
I haven't done that in a long time.
Okay. I've been playing more of it now that I've had more time on my hands. So
Dr. Baginski,
Mhm.
have you been into any chess tournaments, or is it just more of like for fun?
You really know the truth? I'm playing against machines on ICC. I think I sent everybody a link on that. Has anybody gotten on ICC at all? No?
Not yet.
Internet chess services, that is the cream of the crop when it comes to chess in general. It does everything. And you want to play computers, they got computers ranked as low to as high as possible. You want lessons, they have all sorts of lessons like how to mate with a king and two bishops versus a king, bishop, knight, king, mate against king. And it'll take you through the in piece. It's called really it's 3-piece to 5-piece in game. So if you have, a rook and a knight versus say a queen and a king on the other side, is there a guaranteed outcome if you move right? And usually, yes, there is, but you have to know how to move right. And it's really your brain's a neural net. It learns a great deal if you're interested. But chess has always been to me this one thing. If people are good at chess, they're good at engineering usually, and the better they are.
My
And if they-
father-in-law plays a lot of chess. He's
Well,
been playing for, I mean,
there's people
30,
that have
40 years, but
a natural affinity. They can pick them. This one student of mine, Stephen Muhammad, who's ended up being an international master. The kid was very quick learner, very bright. I shouldn't say kid, he was a man, and he was in his mid-30s. But he's one of these guys if you're very good at chess, it means you can see a long way in the future. You kind of are very good at analyzing things and then being creative and how to solve problems. And that's what an engineer usually is good at. And they also have good memories.
yeah, he plays all online, but I mean, he'll have like 4 or 5 games that he plays like at top level type stuff. And
Well, you know who Magnus Carlsen is, anybody? All right.
then, yeah,
Magnus
I've heard of him.
He's the world champion, but he's not just the world champion. He's probably the single most incredible chess player, including Bobby Fischer, and who was an American chess king. He was an international champion, and he was. So this guy, I've watched demonstrations. I think it was on 60 Minutes, where he had 20 boards, and he's blindfolded, and these guys, some of these guys, I think, were masters or grandmasters. And he's moving, and he can remember every single piece's position at every single board. That's one of the signs of a very good chess player. They don't need a board. They can remember in their mind. Now, you try this, and you'll find out. Just do one game. Try to don't use a board. Go from E2 to E4. That's the first pawn. White's pawn out. And that's a Bobby Fischer. Then go up there and then move like a Sicilian defense in your mind. Whatever, I don't know what your knowledge of chess is. Do a standard type of operation. Now, if you can see the pieces and you're good, it's fine until which game?
For me, I tend to like strategy card games.
Oh, cards, poker.
Well, I prefer, I would prefer poker, but they won't legalize it in the U.S. unless you live in a state that already legalizes it.
You can play online poker for money. I know that. Right here in Auburn, you can do it easy. If you want to play for money, there's sites in the
It depends
UK.
on,
If you want the truth, now I don't recommend you do this. You know what a VPN client is, right? Go get a VPN, and I can send you the software to do this. A VPN in Hong Kong, someplace. Now you got encrypted service going back and forth from Hong Kong. Well, Hong Kong doesn't restrict anything like that, gambling. Then jump from there and go to, or maybe you don't want to go to Hong Kong. Maybe you want to go to Australia or maybe someplace in Russia.
Yeah, but the issue with that arises when I want to cash out.
Not a problem. What you do is you use Bitcoin usually. And then when you have Bitcoin, you can cash it out, no problem at all. Look, I'm not a gambler and I don't recommend it, but
it's possible.
The people that play poker for money, and there are a lot of them that play online. Right. They make this, it's, when you have a VPN client and you're going to, I don't know, a place like Russia, they keep their server logs for 2 weeks at most, right? By the time somebody figured out that you could have been doing something illegal, they can't get the information anyway. So if you have an encrypted service through these VPN, unless they really wanted to, I don't think they can. I don't know. I guess could.
I'm a little hesitant as well. I had a good amount of money when the whole poker fallout happened about 9 years ago, 10 years ago. They shut all the services down. Yeah, I had about 6,000 or 7,000 tied up.
The funny thing is they do have. There used to be a show, and it was they had all these poker players. What was that called?
Poker After Dark.
Yeah, but there was another one